first see, are there any questions? All right. Well, today I'm going to review the ionization of hydrogen, and then I'm actually going to do homework problem, the last homework problem in class, because I think that looking at what was turned in, I don't think anybody really did it in sufficient detail, so I'm going to do it in full detail. In fact, I might start with that. I think I will start with this fourth homework problem. It's worth seeing in more detail, in full detail. Thanks for racing before us. Okay, well, the electromagnetic field in the Coulomb gauge, and this is the transverse part of the electromagnetic field. In the Coulomb gauge, the longitudinal part is confined to A0, and that is a dependent variable that depends upon the charge and current distributions, charge distribution actually. Epsilon r of k, a sub r of k, e k dot x minus omega t. And here I'm thinking about the Hamiltonian and the field with a time dependence that's associated only with the transverse photons. So this is a universe with only transverse photons, no charge anywhere. By the way, this structure here, which we see all the time in electrodynamics and optics, this really was a sign long ago, probably as long ago as the time of Maxwell, that the right ingredient, the right invariant was of this form. But I guess in those days, they didn't really realize that k was the momentum of the photon and omega was the energy. So they didn't realize that this was a dot product of two four vectors. But it is. FKR is just an abbreviation that I'm using for the square root of h bar over 2 epsilon 0 v omega k, and so I'm doing this in SI units. Okay, the free Hamiltonian is an integral over space, epsilon 0 over 2 e of x and t squared plus 1 over 2 mu 0 b of x and t squared. Okay. And remember, this comes from an integral d cubed x of e dot d over 2 plus b dot h over 2. So that's what this comes from. I don't know. There are sort of 2 points of view for classical electrodynamics. You can think of these macroscopic fields as the fundamental fields, or you can think of the microscopic fields as the fundamental fields. I tend to think of the microscopic fields as the fundamental fields. Anyway, these E and B that appear here E here is minus A dot, and of course P is the curl of A. Okay. So, as you found when you did the homework problem, these, when you take this expression for the electromagnetic field, create the electric and magnetic fields, and then substitute into here, you get a huge mess. And in that mess, you see things that are simple and things that are complicated. And what you want is to have the complicated things cancel. So the electric part of the Hamiltonian, which is E cubed x epsilon 0 over 2 E squared, or since we substitute for E A dot, let's just do that immediately, that's A dot squared. And so this is going to be epsilon 0 over 2 D cubed x, and now it's a sum over K and R, FKR. And now just carrying out the differentiation here, with respect to time, you get minus I omega K, epsilon R, A sub R of K across. If I write everything down, we'll be here all day and all night. By the way, let me just mention something. This situation with swine flu is, according to the media, getting more and more serious. So if any of you feel sick, don't come to class, all right? Stay home. And tell your friends also. Also, it's a good idea during this outbreak, whatever it is, to wash your hands in soap and water a lot. That's one of the ways you can protect yourself from getting sick. And if you happen to be one of the few Americans who has easy access to an actual doctor, ask the doctor for a prescription for Tamiflu. You might want to fill the prescription. Well, I wouldn't say you should fill the prescription, but it'd be nice to have a prescription on hand so that you could fill it. Assuming pharmacies don't run out. Tamiflu, let me write it. This is the trade name of Roche's product.
What is that stuff? Tamiflu?
Tamiflu, T-A-M-I-F-L-U. It's they're capsules it's an anti-flu medication that works against swine flu. It doesn't prevent it and it doesn't cure it, but it means instead of being sick for 8 days, you're sick for 4 days, something like that. And instead of being deathly sick, you're just sick. I was going to say something else. Yeah, how many of you had flu shots last fall? Oh, hands have gone up. Not good. The flu shot of last fall protects somewhat against swine flu. I get flu shots every year. I'm going to go on to this board now. A dagger e to the minus I, k dot x minus omega t. Okay, that is dotted into, dotted into the sum k prime r prime f k prime r prime minus I omega prime epsilon r prime a sub r prime e to the I k prime dot x minus omega prime c plus I omega prime epsilon prime star a prime dagger e to the minus I k prime dot x minus omega prime t. Okay, so that's the expression, and it's of course one might say in some of the modern slang, it's a piece of work. Anyway, we have d cubed x e to the I k dot x plus I k prime dot x. This is equal to the volume times delta of k minus k prime. And another volume integral is e to the I k dot x minus I k prime dot x is v delta k prime. So we have these Kronecker delta relations, and these help a lot. But what we get is still a mess, because this is then equal to three terms. Epsilon 0 over 2 sum on k r and r prime minus omega k squared. I'm writing in all these factors of, I'm turning f into these h bar things. And that's h bar v over 2 epsilon 0 v omega k. And this is then epsilon r of k dot epsilon r prime of minus k, a sub r of k, a sub r prime of minus k, a sub r prime, that's right, minus k, e to the minus 2I omega kt. Omega depends just on k squared, so whether the k prime is k to minus k, you get the same omega. Okay, so this involves a dot product of epsilon r of k with epsilon r prime of minus k. The second term here is epsilon 0 over 2 sum of k, r, and r prime minus omega squared h bar over 2 epsilon 0 omega k. Well, in this case, I cancel these. And this is epsilon r star of k dot epsilon r prime minus k star. The creation operator, a r of k, a r prime creation operator of minus k, e to the 2I omega kt. All right, so these are terms that we want to get rid of. And then finally, there's a term that's kind of a nice term that we want to keep, epsilon 0 over 2, sum on k and r, omega k h bar over 2 epsilon 0. So here, you see I canceled the omega squared omega, so we just have one omega. I could have canceled the epsilon 0, so we'll do that in the next stage. This is then a sub r of k, a sub r dagger of k plus a sub r dagger of k, a sub r of k, and there's no time dependence at all here, which is a sign of the thing that we want to keep. What I used here to get there is that epsilon 1 of k dot epsilon 2 of k, well, of course, is 0, and in fact, more generally, epsilon r of k dot epsilon r prime of k is delta of r prime. Okay, so that's where we are with the electric field squared. And now if we do the same thing with magnetic field squared, well, it's more complicated. Because you're taking the curl, see, this is the vector part here. And if you're taking the curl of epsilon times that, let me just say this explicitly, del cross of epsilon e to the I k dot x, well, this turns out to be I k cross epsilon e to the I k dot x. So we're going to use this several times in evaluating the magnetic field. And so that's going to give us H0F magnetic is 1 over 2 mu 0 sum on k r and r prime h bar over 2 epsilon 0 omega k. Now we have k cross epsilon r of k. That's the vector, and that has to be dotted into k cross epsilon r prime of minus k. And this is an a sub r of k, a sub r prime of minus k, e to minus 2i omega t. So that's one term. Another term is 1 over 2 mu 0 sum k r r prime h bar over 2 epsilon 0 omega k. And this is now k cross epsilon star of k dotted into k cross epsilon star of minus k, a dagger sub r of k, a dagger r prime minus k, e to 2 I omega k t. Okay, and then the last term, the one that actually you want to show somebody, is sum over k r and r prime h bar over 2 epsilon 0 omega k, k cross epsilon dot k cross epsilon star, and I might just say r of k, r of k, and then this is a sub r of k, a dagger sub r of k plus a sub r dagger. Okay, so that's the expression. And once again, we want to cancel somehow the complicated terms and keep the simple terms. So this is one of the homework problems that I think was too hard. Okay, at this point, I mean, it's well and good to say, well, obviously all the complicated terms cancel, and they do. But to show it, well, the easy way is to recognize that you don't have to use complex polarization vectors. You can choose to use real polarization vectors, and basically what you're doing is you're saying that a sum of epsilon r, a sub r of k over r complex, and let me put sort of, all right, is equal to a sum e sub r, here, this is of k, e sub r of k, a sub r of k, or maybe I should say a sub s, real. In other words, this structure, sum over the polarizations of the complex ones, is the same thing as the sum over the real ones, and you can choose to use the real ones. Okay, so once you use the real ones, you of course have, well, even if you don't use the real ones, you have epsilon r of k dot epsilon r prime of k is equal to 0, and epsilon r of k dot k is equal to 0. And now you also are at liberty to choose how these epsilon, which you call epsilon 1, which you call epsilon 2, and how they're pointing. And so one nice way of doing this is to say this is the vector, say, k hat. That epsilon 1 is in the x direction, and epsilon 2 is in the y direction. And in fact, I put a hat on k just to make it a unit vector, but we know these epsilon vectors are also unit vectors, so I really should have put hats on them like that. So that's one way of choosing these. You don't have to choose them that way, but that is one way. And if you do choose them this way, you notice that k hat dot epsilon 1 hat is equal to epsilon 2 hat, and that k hat cross epsilon 2 is equal to minus epsilon 1. Okay. But we have to deal with these minus k's. And so now what you do is you take this triplet here, and let's keep track. 1 is my, of course this is the left hand. I hope this works with left hand. 1 is my thumb, 2 is my big finger, and my index finger is the vector k. We now go to the minus direction. It looks like that. So 1 is going this way. So it looks like this. K is going this way, or minus k if you want. Epsilon 1 is sort of this way, and epsilon 2 is going that way. And what I chose to do was to rotate them a little bit more around so that epsilon 1 was going in the x direction, and then epsilon 2 hat is in the minus y direction, and minus k hat is down like that. So that's what it looks like, and over in this direction would be minus epsilon 2 hat of minus k. And this is minus k, and this is minus k. So that's what they would look like. And any questions about this? This is the part where you're in danger of fracturing your wrist. All right. So now what we have is minus k hat cross epsilon 1 and minus k is epsilon 2 of minus k, which, by the way, if we now compare this diagram with that diagram, we see that epsilon 2 of minus k is minus epsilon 2 of k. Well, I don't think we need the hats on the epsilons. We know they're unit vectors. Minus k hat cross epsilon 2 of minus k. So that would be this, is minus epsilon 1 of minus k. And that is the same, that is minus epsilon 1 of k. All right, so we have this choice here. I just wanted to make a little more slack in the line in case I trip on it. I don't want to damage the laptop. Is there an extra plug in there? Is that just the one? That's just the one. All right. Well, let's look at. I'll be done here in just a second. So epsilon 1 of k, let's just look at all the other relations that we need. Epsilon 1 dot epsilon 1 of minus k turns out to be 1. Epsilon 1 of k dot epsilon 2 of minus k is 0. Epsilon 2 of k dot epsilon 1 of minus k is 0. And epsilon 2 of k dot epsilon 2 of minus k is minus 1. Okay, so these are the relations that we need. Now, if we use these relations, we see back here for epsilon 0e, we have epsilon r of k dot epsilon r prime of minus k. But we see that by our choice of real polarization vectors, this is 0 if r is not equal to r prime. And if r is equal to r prime, it's sometimes 1 and sometimes minus 1. And so what we get, all right, I think I'm clear now. What we get here is H0 field electric part is a quarter, a sum over k, minus h bar omega k, and we get a1 of k, a1 of minus k, minus a2 of k, a2 of minus k, e to minus 2 omega t, plus a quarter sum on k minus h bar omega k, a1 of k, a1 of minus k. Well, these should be daggers. Big typo. Pen loose so I can. Okay, and then the last term, of course, is the term we like, sum on k, h bar omega k, and this one hasn't changed at all, a over k, a over dagger, okay, so that's the electric field energy. Let me just get some more here. Now, for the magnetic field energy, we need to compute what the dot products are of all of these k cross epsilons dotted into minus k cross epsilon of minus k. And so we first work them out. K hat cross epsilon 1 of k dot k hat cross epsilon 1 of minus k. Well, this is epsilon 2 of k dot into minus epsilon 2 of minus k. And this is epsilon 2 of k dot epsilon 2 of k. So this is actually for 1. The next one is k hat cross epsilon 1 of k dot k hat cross epsilon 2 of minus k, and this is epsilon 2 of k dot epsilon 1 of minus k, and this is epsilon 2 of k dot epsilon 2 of k, dot epsilon 1 of k, and then 0. And similarly, k hat cross epsilon 2 of k dot k hat cross epsilon 1 of minus k. Well, let me just do this one explicitly because I might have gone too fast for the others. So we got k cross epsilon 2 of k is minus epsilon 1. And k cross epsilon 1 of minus k, k cross epsilon 1 of minus k is going to be epsilon 2 of k. In any case, it's 0. Let's see, in my notes I have an extra minus sign there. Maybe I just write. Right. Okay. So this is correct. I just skipped something. All right. The last one is k hat cross epsilon 2 of k dotted into k hat cross epsilon 2 of minus k, and k hat cross epsilon 2 is minus epsilon 1. Okay. And k cross epsilon 2 of minus k is epsilon 1 of k. And so this is equal to minus 1. Okay. So with these relations, we can compute what the what H0FB is. And it is, well, to do that, we're going to use the relation epsilon 0 mu 0 is 1 over c squared. That's that magic relation that I guess for most of us was maybe the high point of freshman physics. But anyway, so what we get is c squared over 4 times the sum h bar k squared over omega k. And remember that omega k is equal to kc. So you see, ck is just going to give us an omega k squared. So this just gives us a1 of k, a1 of minus k, minus a2 of k, a2 of minus k, e to the minus 2i omega kt. And if we take advantage of that relation, we get a quarter sum on k of h bar omega k. And now this is a1 dagger of k, a1 dagger of minus k, minus a2 dagger of k, a2 dagger of minus k, e to 2i omega kt. And then finally, a quarter sum on k, h bar omega k, a sub r of k, a sub r dagger of k, a sub r dagger of k, a sub r of k. Okay, so by the way, the EU has advised people not to fly to the United States. Okay, well, what you see here is that these unwanted terms cancel. If we look at the annihilation part, we get A1 with a positive sign. We look over here, we get A1 with a negative sign. We get A2 with a positive sign here, we get A2 with a negative sign there. For the creation operators, the A1s have a positive sign here, negative sign there, the A2's a positive there, negative here. So they all cancel. And so what we get then is that H is simply, or H0F is simply a half sum over K, H bar omega K, H of R, well, let me write them backwards. So we get that very nice expression. And remember the commutation relations that we have are a sub r of k, a sub r prime of k prime dagger is delta r prime delta k prime. So those commutation relations allow us to rewrite this as a half sum h bar omega k times a sub r dagger of k, a sub r of k, plus a half, and of course I screwed up this one here. So that's the standard form of the Hamiltonian that we've been using, and this part here just counts the number. This is sort of the number operator. Maybe I should play this capital N of K and R. This counts the number of photons of momentum K, or wave number K, and polarization R. and then that total number gets multiplied by h bar omega k, which is the energy of each photon of that momentum. And then we've got this curious thing that's left over, and that is still a mystery. I might mention that if we were doing fermions, we'd get exactly the same expression. We have a sum over k h bar. Well, this is actually a sum over k and r, I should say, index r. We have a sum over k and r, h bar omega k. We have p sub r dagger of k, p sub r of k minus that. And so the big hope with supersymmetry, which I don't know how long this hope lasted, a millisecond or a few years, was that these guys would cancel. It's perhaps not totally a hope in vain, because you can imagine there might be the same number of modes, as the same number of boson modes as fermion modes, in which case the worst part of this thing cancels, because this omega k, of course, is the square root of k squared plus m squared, where m is the mass of the particle, zero in the case of photons. And so as you look at the worst part of this divergence, it's the k squared, not the m squared. And so the worst part of the divergence does cancel when you have the same number of fermion modes as boson modes. Now, whether that's true or not, or whatever are the fundamental particles, nobody knows. People tend to think at every era that the particles they last discovered are the fundamental particles. This has always proved to be false in history, and I don't think there's any real reason to bet that the quarks and leptons are fundamental. They may be, but they may not. And I suppose if you're asking Congress for $10 billion for an accelerator, then it's good to say that these are the fundamental particles. If instead you say these are the latest messes that we've found, it's maybe less. All right. Well, I think that is it. Right. So I'm going to Xerox 2 copies of these notes together. All right. If anybody wants an extra copy, I've got it here. All right. Are there any questions about this? I do have chalk. I forgot to bring the crackers today. I've got crackers at home. Does anybody want anybody have a question? It's chocolate. All right. I think it's worthwhile seeing this at least once in the class. All right, so we're back to hydrogen. So once again, H0 atomic, or H0 matter, is P squared over 2m minus E squared over 4. What am I saying? E squared over R. And if we put this in SI units, which is P squared over the reduced mass m minus, let's see, E squared over 4 pi, or Q squared over 4 pi epsilon 0 is E squared, and E squared is alpha H bar C. Okay. So this Q squared, I should have called this Q squared. Q squared is equal then to 4 pi epsilon 0 alpha H bar C. Oh, but this thing would be Q. All right, let's see. I haven't changed from the units here. So this would be Q squared over 4 pi epsilon 0 R, and this then turns into P squared over twice the reduced mass minus alpha H bar C over R. That's the way it goes. And the final state has a wave function xp, which is e to the I p dot x divided by square root of v, or p dot x over h bar, I should say. So this is the same thing. This is the I k dot x over square root of v. K is box quantization. We're doing box quantization for the electron as well as for the photons, and v, of course, is Q. So the initial state is the 1, 0, 0 state of hydrogen, and then some photon. I should probably use K for the photon and P for the electron in its final state. The final state is P, so we're looking at this transition. And so what we have is P S T0 1 0 0 K is equal to minus I over H bar and integral 0 to T of P e to the I H0 matter plus H0 field T prime over H bar. We have then minus Q over M A dot P as the interaction, and then e to the minus I H0 matter plus H0 field T prime over H bar, and the state 1 0 0 K T prime. So that's the expression. And of course we now have our formula actually derived now for the Hamiltonian of the electromagnetic field. And so A is written down way over there, and so what we have then is IQ over H bar M integral 0 to T, and the final state here is going to be well, let's just say e to the I EF minus E100. EF is the energy of the final state electron, minus H bar omega K T prime over H bar. So I've gotten all the time factors in, and now we have P A dot P 1 0 0 K dt prime, and now you remember in the Coulomb gauge we can put the P on either side, and that P then is just going to pull out this P. So in other words, to do the matrix element, what we have here is a P. We then have a sum. We're just going to use annihilation operators, K R, H bar over 2 epsilon 0 v omega k to the 1/2 times and epsilon r of k, ar of k, e to the I, k dot x minus omega t. Let's see, we've already pulled out that t. So what we have here is a time-independent matrix element, k dot x, and then 1, 0, 0, k. And in our box quantization, as we sum here over k, only one term contributes. As we sum over k and r, only one term contributes, corresponding to the k and r of the initial state. And so this thing gives us h bar over 2 epsilon 0 v omega k to the 1/2. And so then we have p. I left out the p. P dot. P operator dot epsilon r of k e to the I k dot x 1, 0, 0. So this has annihilated that photon. This pulls out the p final. So we get this big square root here times p final dot epsilon r of k. And now we have a matrix element. And the matrix element is p e to the I k dot x 1, 0, 0. So this is an atomic matrix element that we can calculate. And we might as well try to do that now. Let me see, before we do actually compute that, let me use this nice bit of clean blackboard here to remind ourselves of the delta function relation. I always keep forgetting this. So we have limit of sine squared. Let's just say that when we integrate this thing, in fact, let me just do the integral. We get I, well, the IH bar is going to cancel. So we're going to have just Q over M, this huge square root, P dot epsilon, the matrix element, P, E, D, I, K dot X, oh, no, that's all right. P 1, 0, 0 have times this integral, and this integral gives us e to the I, e final minus e 1, 0, 0 minus h bar omega k t minus 1 over the energy denominator after canceling the I over h bar. EF minus e 1, 0, 0 minus h bar omega k. Okay, when we square this thing to get the probability, okay, then the P of t is Q squared over M squared H bar over 2 epsilon 0 V omega K times P dot epsilon squared times the matrix element P e to the I K dot X 1, 0, 0 squared. And then we have a 4, and then times sine squared of EF minus E 1, 0, 0 minus H bar omega K T over 2 divided by the energy denominator. That's H bar omega K squared. And our delta function relation, well, a delta function relation is that this structure here turns into pi t over 2h bar delta of EF minus E100 minus h bar omega k. So the rate then, which is, so in other words, E of t is equal to well, the 4 goes because we have a 2 here and a 2 there, and so it's q squared over m squared h bar over epsilon 0 v omega k p dot epsilon squared matrix element p e dot k dot x 100 squared, and then a pi and a t and an h bar, and the h bar cancels that h bar. This. Okay, so then the transition rate apart from final states is the derivative of this, which we call times the delta function, times delta of E final minus E100 minus h bar omega k. And so then this rate is q squared of pi q squared over m squared epsilon 0 v omega k p dot epsilon squared t e v I k dot x 100 squared delta of EF minus E100 minus h bar omega k. Okay, so that's our formula for the rate. But we have to sum over initial polarizations, integrate over final states, and when we integrate over final states, we have to sum over momentum of the electron and over its polarizations, and the two spin possible polarizations. Okay. I need this anymore. Okay, so what we've got then to calculate this matrix element, P EVI K dot X 100. Now, of course, we made the dipole approximation. This would be a disaster because we just replace. Well, it wouldn't actually be a terrible disaster, but it wouldn't be a good approximation because K now, instead of being an optical photon of a 1, 2, or 3 MeV, 1, 2, or 3 EV, is a photon of at least 13.6 EV, and it might be 50 EV or 100 EV, and so in that case this wouldn't be such a good approximation, a dipole approximation. So we're going to actually do this correctly, and so what we have then is we're going to insert a complete set of states. So we have Px EVI K dot X. Remember, this X is really X operator, and so it feeds off this X. And then we have X 100. So that's our matrix element. And so this is equal to integral d cubed X E to the minus I P dot X over H bar over the square root of V, e to the I K dot X, and then what's left is R10 of R over the square root of 4 pi. That's the ground state hydrogen atom wave function. And okay, so in other words, maybe I should write this down separately. X100 is what I just wrote down, and the rest of that, if we keep the z, so this is, we're considering the case, we can do almost exactly the case of a nucleus of z protons and 1 electron. Not the most realistic case for advanced matter physics. Z over A0 to the 3 halves, A0 being the Bohr radius, e to the minus ZR over A0. So that's our hydrogen atom wave function. And so this whole thing then becomes 1 over the square root of 4 pi v, 2 z over A0 to the 3 halves, integral dqx, e to the minus I q dot x. I'm letting q equal k minus p. P is the momentum of the electron, and oh wait, I've got things in. Let's see. I better call this h bar k. Let q be. No, it's actually the other way around. I want to get rid of the h bar. So q is k minus p over h bar. This is the p over h bar. So this is e to the minus I q dot x minus ZR over A0. And, all right, so that's our integral. And, of course, doing the angular integration, we get a 2 pi from the d phi integration. Then we integrate minus 1 to 1 d cosine theta. And so this is then let me just say 4 pi over the square root of 4 pi v. Cancel the 4 pi's. Z over A0 to the 3 halves. Now we're integrating 0 to infinity dr r squared. That's the volume integral. Integral minus 1 to 1. Let me just call it x for cosine theta. E to the minus I q r x minus ZR over A0. All right. So that's the integration, and so what are we calling this, by the way? We're calling this the matrix on. Okay. So we've got then this P e to the P e to the I k dot x 1 0 0 then is I'm going to write this square root of 4 pi. Square root of 4 pi over v. Z over A0 to the 3 halves, and then integral 0 to infinity dr r squared e to the minus dr over A0, and times what the result of doing the x integration, which is e to the minus iqr minus e to the iqr over minus iqr. And so altogether this is square root of 4 pi over v 2 z over A0 to the 3 halves 1 over q integral 0 to infinity dr r sine qr. So the 2 came from putting the 2 down here and making that into a sine. And of course, e to the minus cr over a0. Well, this is a nice convergent integral. And so altogether, this is giving us 2 square root of 4 pi over v z over a0 to the 3 halves, 1 over q, and the rest of it is 2qz a0 cubed over z squared plus q squared over a0 squared squared. So that's actually the matrix element. Now we have to put that matrix element into our formula over here, which is right here. So let me go over to this board here and erase. Are there any questions or corrections? I mean, I've been doing the change of units on the fly, so possibility of a mistake is not 0. All right, so let's put it together to get W hat. Then W hat. Let me put on my glasses so I can use it better. W hat then is pi q squared over m squared epsilon 0 d omega k p dot epsilon r of k squared. Then this matrix element, which is, because I should have written that stuff forward, but never mind, I'll put it here. Yes? Yes, but can you call me in about half an hour? Great, thanks, bye. No idea. Okay, 2 square root of 4 pi over v z over a0 and 3 halves 1 over q, or 1 over q to q is kind of silly. There's also a 2. Let's clean this up a little bit. Or the q's cancel, z a0 cubed over z squared plus q squared a0 squared squared. All right, I think that's right. Now, we have to integrate this over the final. Oh, I forgot the delta function. Delta of E final minus E100 minus H bar omega k. And we have to integrate this over the density of final states of the electron. And the sum over n, goes to L over 2 pi cubed integral d cubed k plus a sum over the polarizations. So this is sum over r d integral d cubed, and this is d cubed p here, over, well, wait a second, d cubed p over 2 pi cubed, 2 pi h bar cubed. So d cubed p over 2 pi h bar cubed. And so we have to integrate this thing over that. So the actual rate then is the integral of this times v dqp over 2 pi h bar cubed and summed over polarizations. Okay, well, the integration, what we've got in here is a delta function of E is here p squared over 2m, so dE is p dp over m, and in terms of k, that's h bar squared k dk over m. And so now that we've translated it back into k, well, the trouble is I wanted to keep k as the momentum of the initial photon. So maybe I should stay in these with this term and not use that, because that k is going to get us confused. So this dq, this dqp is equal to, of course, dp d cosine theta, and then p squared dp, which is then d omega, and p dp is m so it's right. So we have p squared dp, and so that's pm dE. All right, so that goes into here, and in fact we could stick it in there right away by just saying this is d phi d cosine theta over electron, or better yet, d omega pm dE final. And now the dE final cancels this delta function, and so the delta function goes away, and we simply have that the momentum of the electron is whatever was left over from the momentum of the photon. And so now we've got this huge quantity here. So why don't you guys help me cancel these things? We've got a sum over the polarizations is just going to give us a 2 for the polarizations of the electron, because the electron polarization vector didn't appear in any of this. So this is 2 pi q squared over m squared epsilon 0. The v's cancel. M squared epsilon 0 omega k. And then we have P dot epsilon R of K squared. Let's see, we've got also a 4 square root of 4 pi. Let me just put that in. Actually, it's square root of 4 pi over b, because we didn't cancel the v from the square root there. We then have z over a0 to the 3/2, and not a z0, z, and then another z, a0 cubed over z squared plus q squared, a0 squared, and then we've got 2 pi h bar cubed there, and then we have a pm. Well, that m cancels this 2 here. All right, well, that's an awful lot of mathematical foliage there. Let me show you how to deal with the tricky part here. I think the best thing is for me to start from here next time and finish the numerical foliage. But the part that requires a little bit of thought is the P dot epsilon of R. So we have P dot epsilon R of K, and we're squared, or abscess value squared, and we want to average this. Well, remember what I told you about the sum over the photons. This means we sum, this is 1/2 the sum over the photon polarizations. So that's 1/2 sum over R, P dot epsilon R star, epsilon R, actually it's this way, dot P. And then this is to be thought of as a dyadic. And so that gives us 1/2, that gives us 1/2 P dot, the 3x3 identity matrix minus K hat transpose dot P. So that's what happens to this particular sum. And so that is to say P dot epsilon squared, averaged over initial polarizations then, is 1/2 P squared minus P dot K hat squared. And if you think of so let's get the angles right. Let's suppose K hat is in the z direction, then this is P cosine squared theta. So this is then 1/2 P squared 1 minus cosine squared theta. So it's altogether 1/2 P squared sine squared theta. So that's what happens to this. That becomes 1/2 P squared sine squared theta. And I think that it's one thing to change the units on the fly. When they get this complicated, I think I better just let it go to the beginning of the next hour. The one to stop. Any questions? All right, well, we have to talk with the operator, but we should